Same thing as the previous section. So we know lots of different words for the same thing. Finding an instantaneous velocity, finding the slope of a tangent line, finding a derivative. It's all that same basic limit of the slope. And in section 2.7, we are doing them with a's. In section 2.8, they kind of switched to x's. And we're really just using that one definition where it's limit as h approaches 0, f of x plus h minus f of x all over h. So we're getting lots of practice with that calculation. So we ended Friday, we were talking about derivatives. We looked at some on the graphs. So we'll start looking at differentiable functions. So a differentiable function is just one where the derivative exists. So if you can take the derivative, it's differentiable. And sometimes it's possible that it's differentiable on the entire graph. The entire thing has a derivative. And sometimes it's just a specific interval, because there might be one point where the derivative doesn't exist. So let's look at this problem. I want to figure out where the absolute value function is differentiable. That means, where does the derivative exist for the absolute value function? So remember, every time I gave you absolute value, we rewrote it using the piecewise definition. All right, and if you put in something bigger than 0, so if you put in a positive, what's true about the derivative? Or about the absolute value? It's still positive, right? So it doesn't change it. And if you put in a negative, the absolute value makes it positive, so you get the opposite of what you put in. So this is the definition we have used every time we talk about those derivatives. All right. So let's try to actually work it out then. So if x is greater than 0, then if I did the derivative, remember we said this notation means derivative, that's the limit as h approaches 0, f of x plus h, so if we're talking about greater than 0, my function is just x, so f of x plus h would just be x plus h, minus f of x, which is just x, all over h. You guys with me there? So at that point, what do we do? What happens? X's cancel. So we have h over h, which is just a 1. And there's no h to even plug in for, so this limit is 1. So what that means is, if you're putting in a positive number, the derivative is always equal to 1. Second option, if we put in a negative number. So that means we're down here on this section. So in that case, we go on it as h approaches 0. F of x plus h, that would be the opposite of x plus h, minus f of x would be the opposite of x, all over h. And if you put in your negatives, so you'd have negative x minus h plus x, so the x's drop. Negative h divided by h is negative 1. So this is equal to a negative 1. Here's what's happening. The derivative, you think about the absolute value function, a derivative is the slope of the tangent line, right? If you took your absolute value for all the positives, that's just a line with a slope of 1. So we're getting out 1 the whole time. The other side, the negatives, that's line would have a slope of -1. So the derivative is giving us -1 the whole time. But 0 should technically fit in both of those pieces, right? Absolute value of 0 is 0. And you can't get out two different answers. So what happens is this derivative doesn't exist at 0. Because the two pieces don't match up, there's no way to connect them. So this one does not exist at x equals 0. So it's not differentiable at 0. There is no derivative there. Because the left and right hand limits don't match. We're getting out two different things. So if we think about what happens here, we know this derivative has a break in it, right? That's not continuous. In general, if something is differentiable, that means the original function was continuous. Now, the reverse is not true. Just because it's not differentiable does not mean that the function wasn't continuous. There are other things. And if something's continuous, that doesn't mean the derivative exists. If you think about the absolute value, is absolute value continuous? Yes, but did the derivative exist at 0? No. But if we have a derivative, then the original thing had to have been continuous. So that brings up kind of the point, what things make the derivative not exist? So that's kind of the next piece that we're going to look at today. So the absolute value, if we think about it, 0 is the place where the derivative didn't exist. And that's actually because of the sharp corner. Anytime you have a corner, the derivative doesn't exist because there's not a single tangent line that would exist there. If it's rounded, like a parabola, you can draw a horizontal tangent line. But when it's a corner, there is not. So the first thing, if there is a corner, then it's not differentiable. So looking at a graph, anytime we have a sharp corner, there would be no derivative there. The second thing, we know that if the derivative exists, it had to have been continuous. So if there's a place where it's not continuous, then that would be a place where there is no derivative. So vertical tangent lines, it would be a place, and jump discontinuities, or really any discontinuity, would be a place. So things that make it not differentiable, no derivative. When you have a corner, a break in the graph, and a vertical tangent. Those make the derivative not exist. Kind of looking at some graphs. Okay, this is a vertical tangent right here. So there is no single perfect tangent line right there. Even this is like a vertical tangent line. So vertical tangent line, there is no derivative. These are showing you a corner. This one, there's a discontinuity, the vertical tangent. Those are the things that make the derivative not exist. So I would probably put a big star next to this. As we continue to go through derivatives, we'll have to talk about when would we not have a derivative, and those are the three pieces. We're going to go ahead and keep going. So we can do higher derivatives. We've only done the first derivative, but you can do a second, a third, a fourth. You just keep repeating it. Typical notation you might see is this, d squared y over dx squared, or you might see like f double prime of x. Those mean second derivative. Do the derivative twice. And basically, we do the whole limit thing, we get our answer, and then we do it again with that answer. So let's look at one. I believe did we do this example on Friday, x cubed minus x? That was example 2, right? So from example 2, the derivative of this, the answer we got on example 2 was 3x squared minus 1. So I'm not going to rework that, we did that one on Friday. So when I want the second derivative, I'm going to do the limit as h approaches 0. F of x plus h, but we're putting it into the derivative this time. So that would be 3 times x plus h squared minus 1 minus f of x, so that's the derivative in this case. So we are repeating with the answer that we got the first time. So if we multiply this out, can I FOIL and distribute my 3 at once? So we would get 3x squared 6xh plus 3h squared and then minus 1. Distribute that negative, so minus 3x squared plus 1 over h. So the 3x squared and the 1's drop out. We can take an h out of everything, so that gives us 6x plus 3h. If you plug in a 0, you get 6x for the second derivative. It's not true with every function, but with polynomials, the more derivatives you do, the nicer your answer becomes. So you usually lose terms as we go through. So what this is representing, we know a derivative is the slope of the tangent line. So it's saying the second derivative is saying if you graphed the first derivative, it's the slope of the tangent line on that graph. In terms of position, that's an example we've used a lot. We know S of t represents position. The first derivative is velocity, or kind of like your speed, telling you how your position is changing. If you look at how your velocity is changing, what would that be? If we're looking at the slope of it, so think about like your speed when you're driving your car. If you look at how fast your speed is changing, that's your acceleration. The third one we don't look at as much, but it's actually referred to as jerk in physics if you continue doing those in relation to position. So the notation kind of stays the same. If you want a third derivative, we do 3 tick marks, or you might see the d3y over dx to the third. After that, it becomes kind of annoying to count tick marks, so after that they just put the number. So if they want the fourth derivative, they would probably just put f4 of x. So first 3 we do tick marks, after that we just write the number for higher derivatives. So using the same function we just did, let's do the third and fourth derivatives. So we know from example 2, the first derivative was 3x squared minus 1. then in example 6, we got that the second derivative was 6x. So the third derivative, we're basically repeating the limit with our answer to the second derivative. So the limit as h approaches 0, f of x plus h minus f of x all over h so if we distribute our 6x is canceled, so we have 6h over h. And so we just get 6 for the third derivative. So that means that, if you think about it, the second derivative was just a line. If you're thinking about the slope of this line, slope of the tangent line, since it's the line itself, it was just the 6. And that's what we got.
Wasn't there earlier when as transferred to some number of the constant?
The constant.
It's the constant.
So if I wanted the fourth derivative, f of x plus h, my function is just 6. So there's nowhere to even plug in an x plus h, so f of x plus h is still 6. Minus f of x is 6 all over h. 0 divided by h is 0, so my fourth derivative is 0. Which makes sense if you think about it. If you just graph 6, that's a horizontal line, isn't it? What's the slope of a horizontal line? 0. And after that point, once you get a 0, any derivative beyond that would continue to be 0. It's not true with every function, but with polynomials, you will always hit this point. At some point, it would become a 0. And then after that, every derivative would be a 0. All right. Any questions there? Let's jump to, we did those 2 examples on Friday. Let's look at this one. So we'll do the last few examples and give you guys time to work. So this graph is showing how driving speed affects your gas mileage. So my x-axis, that's my speed. My y-axis is the mileage. What is the meaning of the derivative? So a derivative is a rate of change, right? It's a slope. Think about when you do slope, you do change in y over change in x. My y-axis is miles per gallon. What's my x-axis? Miles per hour. Okay, if you put those together, how do you divide fractions? So we have the first times the reciprocal. And so our units there are hours per gallon. So if I asked you for the units, I think on the previous homework we had something that asked you for units. That's kind of how it works. It's just like finding the units of a slope. So the units of this derivative would be hours per gallon. What is it telling us? A derivative is an instantaneous rate of change, or an instantaneous velocity. So the derivative instantaneous rate of change in our y, which is our mileage, in terms of x, which was the speed. Okay, or it's like telling you at a particular point in time, how is your mileage changing? Okay, it would give us hours per gallon. How many hours would you make it on a gallon of gas in that case? So if I wanted to sketch the derivative, that's something we kind of practiced a little bit on Friday. And I told you to first look for any place where you would have a horizontal tangent line. So any maximums or minimums, which looks like about right here. So that would be a 0. We did do that one example where you were actually like measuring slopes, but let's do this one a little more informally. We know this whole point is increasing, so the derivative should be positive. Here, it's not increasing very quickly, so what's my derivative doing? It's kind of flattening out, yep, so this is kind of our steepest point. So if we look at that, but then once you get to about here, you know, it's going to be flattening out and getting closer to 0. So very informal graph with something like this. After that point, our mileage is decreasing, so the derivative would be a negative. No, not a very accurate graph, but we have the correct shape. So at what speed should you drive if you want to save on gas? That is kind of our optimal. So we would want to know when our derivative was 0. Because what this is saying right here is saying at this point, as long as you're driving faster, your mileage is still improving. So while it's good to be in this area, you can do better. But once you hit this point, going faster makes your mileage start dropping off. So the optimal is 50 miles per hour. Questions there? Let's look at this one. Where is this graph not differentiable? So where does the derivative not exist? What are the 3 cases that make a derivative not exist? A discontinuity, a corner, and the vertical tangent, which is also a type of discontinuity. Okay, so where would it not have a derivative? At 3. The reason is it's a corner. What's one more place you wouldn't have a derivative?
0.
And the reason is, you could say discontinuity or a vertical tangent line, either one. You'll notice these are all taken from the book. That's where the numbers come from, so that kind of tell you which problems they're similar to on your homework. So this is giving us, we have 4 graphs, and they represent an original function, first derivative, second derivative, and third derivative. We have to figure out which is which. Isn't it? Okay. We're dealing with polynomials right now. And with polynomials, we saw that one that we went like to the 4th derivative. As you do your derivatives, they become simpler. So as a general rule, try to find the one with the most terms in it. It's not guaranteed to be the first function, but it's likely. So which of these 4 has the most terms in it? D. Okay, so let's start with D. All right, I know D would have a horizontal tangent line here and here. So that means its derivative must be 0 in those 2 places. My function was increasing until I got to this point, so the derivative should be positive. Between those it was decreasing, so the derivative would have to be negative, and after it was increasing, so derivative has to be positive. So which one has to be the derivative of C, or of D? C. Okay, so we know, even if D isn't the first one, that C comes after it. So let's talk about C. It only has a horizontal tangent here, right? Before that point, it was decreasing, so the derivative would have to be negative. After that point, it was increasing, so the derivative would have to be positive. So which graph would that be? It has to be negative and then positive, so that's graph B. All right, looking at B. The only place it has a horizontal tangent line is right in the middle. It was increasing before, so the derivative has to be positive. Increasing after, so the derivative is still positive, so that has to be graph A. So that means D is the original, C is the first derivative, B is the second, and A is the third. My reasoning is just what we talked through. I'm not going to write all that down, but we looked at where you have horizontal tangent lines and increasing, decreasing. So I'm done with the notes for this. We'll probably do a little practice tomorrow, but you will have a large chunk of tomorrow to work on the homework as well. So the assignment from this section is due on Wednesday. Remember, I did print it for those ones where they have you like drawing the derivative on top of the graph. So you have those graphs there in front of you. That might be useful. But you should be able to do all of them at this